Hello students, I am Gulshan Makkar and in this video we will see formation of analytic function. So for this we have two methods, method 1 then method 2 Milnes-Thomson method, and we will see few examples based on these two methods. So if we are given a function f of z is equal to u plus iv, which is an analytic function. So in the first method, suppose we are given f of z is equal to u plus iv and one of the conjugate function u is given to you, and we have to determine the another conjugate function v. And once v and u are known, we can find f of z, which is given by u plus iv. So if u is given, we first find del u by del x and del u by del y. Then using the definition of total differentiation, we find dv is equal to del v by del x into dx plus del v by del y into dy. Now since f of z is analytic, we have the CR equations are satisfied, and the CR equations are given by ux is equal to vy and uy is equal to minus vx. So in place of vx we are writing minus uy, and in place of vy we are writing ux. So this equation is now of the form m of xy dx plus n of xy dy, which we have seen in the first semester, and this is nothing but the general form of an exact differential equation. So if we are comparing these two equations, then m comes out to be minus del u by del y and n comes out to be del u by del x. Now this is an exact differential equation because the condition for exact differential equation is del m by del y should be equal to del n by del x, and this is satisfied because if we are finding del m by del y, then it is minus del square u by del y square, and if we are finding del n by del x, then it is del square u by del x square. Now these two partial derivatives implies del square u by del x square plus del square u by del y square is equal to 0, which is true because u is harmonic function since f of z is analytic function. And if the given differential equation is an exact differential equation, then its solution is given by integral m dx, where we have to treat y as constant, plus terms of n not containing x dy plus c. So this is the solution, and from this equation we can find the value of v. Now if v is given, then first we find del v by del x and del v by del y, and in this case we use the definition of total differentiation for u. So du is given by del u by del x into dx plus del u by del y into dy. So again, by using CR equations we can replace ux by vy and uy by minus vx, and then again we will be getting an exact differential equation which can be solved in the similar manner as we have solved in the first case. Now we will see our second method, which is known as Milnes-Thomson method, and this method is used to find f of z directly without finding the conjugate harmonic function. So if suppose u is given to you and we have to determine the analytic function f of z, then we start with let f of z is equal to x plus iy such that the harmonic function f of z is given by u plus iv. Then differentiating both sides with respect to x, we get f dash of z is equal to del u by del x plus I times del v by del x. Then if u is given, we first find del u by del x and del u by del y, and this del v by del x will be replaced by using CR equations by minus del u by del y, and then we are denoting del u by del x is equal to phi 1 of xy and del u by del y is equal to phi 2 of xy. Then on putting x is equal to z and y is equal to 0 and integrating, we get f of z is equal to integral phi 1 of z0 dz minus I times integral phi 2 of z0 dz plus the constant of integration c. In the similar manner, if v is given to you, then we first find del v by del x and del v by del y, and again from the above equation f dash of z is equal to del u by del x plus I del v by del x. Now we will replace this del u by del x using CR equation, which is given by Vy. So f dash of z will then become psi 1 of xy plus I times psi 2 of xy, where psi 1 of xy is del v by del y and psi 2 of xy is del v by del x. And again putting x is equal to z, y is equal to 0, and integration gives us this equation. So from this we can obtain f of z directly. Now let us see few examples based on these two methods to find analytic function f of z in terms of z. So in the previous video we have seen what are analytic function, what do you mean by harmonic function, and then we have seen the conditions for checking the function f of z to be analytic, and those conditions are known as CR conditions or Cauchy-Riemann conditions. So the Cauchy-Riemann conditions are the necessary conditions to check whether the function f of z is analytic or not. So let us take this first example. Show that the following function is harmonic and determine the conjugate function. Also, we have to find the analytic function f of z in terms of z. So we know that if we are writing z is equal to any complex number of the form x plus iy, then the function f of z is known as function of complex variable z and is given by another complex number w of the form u plus iv, and here u and v again they are functions of x and y. Then if we have to check whether this function is analytic or not, we have to check the CR conditions. So the CR conditions are ux is equal to vy and uy is equal to minus vx. So for this particular functions u and v, we have to check these conditions. Ux is equal to vy and uy is equal to minus vx, and if these two conditions are satisfied, then we will say that the function f of z is analytic function. Also, if we have to check whether u is harmonic or not, then we have to show that this u satisfies Laplace equation. That means we have to check this condition del square u by del x square plus del square u by del y square is equal to 0 or not. So if this condition is satisfied, then we will say that u is harmonic. So for this function u is equal to 2x minus x cube plus 3x y square, we have to first check that it is harmonic function. So for that we have to differentiate u partially with respect to x. So we can write this as ux is equal to 2 minus 3x square plus 3y square. And similarly, we can find the second order partial derivative del square u by del x square by again differentiating ux partially with respect to x. So we will be getting minus 6x. So this is nothing but del square u by del x square. Again, differentiating u partially with respect to y, we get uy is equal to 6xy. So this will imply uyy will be equal to 6x. So from these two equations, this is nothing but del square u by del y square. So from these two equations, adding uxx and uyy, we can observe that the sum is 0 and therefore this function u is harmonic. So adding 1 and 2, we get del square u by del x square plus del square u by del y square is equal to, it is minus 6x plus 6x is equal to 0, and therefore we can say that u is harmonic. function. So this was the first part, show that the following function is harmonic. And next we have to determine the conjugate function. So in the previous video I have told you that if f of z is equal to u plus iv is an analytic function, then u and v are harmonic functions, and those u and v are known as conjugate harmonic functions of each other. So here, to determine the conjugate function, that means we have to find v if u is given, and we have to find u if v is given. So in the second part, to find the conjugate harmonic function, that means to find v, to find conjugate function v. So here we are given that the function f of z is analytic. So if f of z is analytic, the CR equations are satisfied by Cauchy-Riemann equations. What we can write? Ux is equal to Vy and Uy is equal to minus Vx. So we have given u here. So from this u we are finding Ux and Uy. Okay. So to find v, we take the total differential of v. So it is given by dv is equal to del v by del x into dx plus del v by del y into dy. So this partial derivative vx can be replaced by minus uy, and the derivative vy can be replaced by ux. So in place of vx I can write minus del u by del y into dx plus in place of vy we can write del u by del x into dy, which is definitely an exact differential equation. To see the procedure you have to check out my first video, okay? And this differential equation is an exact differential equation, which is an exact differential equation. Now what is an exact differential equation that you can see in the screen? So any differential equation of the form mdx plus ndy will be an exact differential equation if the condition del n by del y is equal to del n by del x is satisfied. And if del n by del y and del n by del x are same, then we will say that this function is an exact differential equation. And in that case, the solution is given by integral m dx, in which we have to take y constant, plus terms of n not containing x into dy. So here we have the values of uy and ux. So we will substitute these values in equation number 3 to get an exact differential equation. So from equation 3 we can write dv is equal to minus of uy, which is 6xy into dx, plus uy, which is 2 minus 3x square plus 3y square into dy. So this is your dv. Now this is an exact differential equation, and therefore its solution is given by v is equal to integral m dx. So it is minus 6xy dx plus integral terms of n not containing x. So we have two terms which is not containing x. So it is 2 plus 3y square into dy, and plus the constant of integration c. So here we have to treat y as constant. So this can be written as minus 6y into x square by 2 plus 2y plus 3y cube by 3 plus c. And on simplification, this will give us minus 3x square y plus 2y plus y cube plus c. So this is the final conjugate function v for the given function u. So in the third part, we have to find the analytic function f of z in terms of z. So we very well know that the analytic function f of z is given by w, which is equal to u plus iv. So we have to put the values of u and v here to get the required function f of z. So this can be written as f of z is equal to u, which is given by 2x minus x square plus 3x y square plus I times v, which is given by minus 3x square y plus 2y plus y cube plus c. So this is the value of f of z in terms of x and y. So to find f of z in terms of z, what we have to do? We have to put x is equal to z and y is equal to 0 in the above equation. So we will be getting f of z is equal to 2z minus z square. We have to put y is equal to 0. So these four terms will become 0 and plus I c. So this is your final answer, f of z in terms of z. So let us take one more example based on Milnes-Thomson method. So this example can also be solved using the first method. So here what is given? If u is equal to y cube minus 3x square y, show that u is harmonic. Again, to check u is harmonic, we have to satisfy this condition, uxx plus uyy is equal to 0. So if this condition is satisfied, then we will say that u is harmonic. So after proving that u is harmonic function, we can use Milnes-Thomson method to find f of z directly without finding the conjugate function v. And once we are finding the analytic function f of z is equal to u plus iv, then by equating real and imaginary parts from this equation, we can obtain the value of v also. So let us begin with this example. So here u is given u is y cube minus 3x square y. So differentiating both sides with respect to x partially, we get ux, which is nothing but del u by del x, is given by minus 6xy, and from this we can find uxx is equal to minus 6y. Similarly, differentiating u partially with respect to y, we get uy is equal to 3y square minus 3x square, and from this we can get uyy is equal to 6y. So again, if we are adding equations 1 and 2, we can say that uxx plus uyy is equal to minus 6y plus 6y. It is 0, and therefore the function u is harmonic. So therefore 1 plus 2 implies uxx plus uyy is equal to 0, and therefore u is harmonic function. Next we have to find the analytic function f of z. So since u is given, we have del u by del x is minus 6xy, which we are denoting by phi 1 of xy. You have seen in the method, and del u by del y, which is given by 3y square minus 3x square this we are denoting by phi 2 of xy. And if we are putting x is equal to z and y is equal to 0 in del u by del x and del u by del y, then we can find phi 1 of z0 is equal to 0 and phi 2 of z0 is equal to minus 3z square. And therefore, by Milnes-Thomson method, we can write f of z is equal to integral phi 1 of z0 dz minus I times integral phi 2 of z0 dz plus the constant of integration c. So this is given by 0 minus I times integral phi 2 of z0 is minus 3z square dz plus c. So this is given by iz cube plus ic. So this is the required analytic function f of z. Now in the last part, we have to find the conjugate harmonic function v. So we have f of z is equal to I times z cube plus the constant of integration c. So we can replace this z by x plus iy, and then we can write this as I times, it is x cube plus 3x square iy plus 3x iy square plus iy whole cube plus c. So this can be written as I times x cube plus 3x square iy plus, or this you can write as minus 3x y square, because I square is minus 1 and I cube is minus I. So it is minus I y cube plus c. So multiply by this I, so it is ix cube minus 3x square y minus 3x y square I plus y cube, because this I and I will become I square and it is plus 1 plus IC. So after collecting the real and imaginary terms, we can get these two are the real terms. So it is y cube minus 3x square y plus the imaginary term I times, it is x cube minus 3x y square plus IC. So this is nothing but u plus iv. So on comparing, we can get, therefore v is equal to x cube minus 3x y square after equating the real and imaginary parts. So this is our final answer. Here you can also observe that we are getting u is equal to y cube minus 3x square y, which was given in your question. So v is equal to x cube minus 3x square y is the required harmonic function. So let us take the third example. Determine the regular function or analytic function whose imaginary part is e to the power minus x, x sin y minus y cos y. So if we are assuming that the required analytic function is f of z, which is given by u plus iv, then we are given the imaginary part of f of z, that is v is equal to, therefore v is equal to e to the power minus x, x sin y minus y cos y. So here we are given v and we have to find the regular function directly. So we can use the Milnes-Thomson method. So since v is given, we can find del v by del x and del v by del y. So differentiating v partially with respect to x, we get, So it is del v by del x is equal to, so since these two are functions of x, so we have to use product rule here. So we are keeping e to the power minus x constant, and derivative of this partially with respect to x is given by sine y. Then plus, keep this bracket as constant, x sine y minus y cos y, and derivative of e to the power minus x with respect to x is minus e to the power minus x. So this is the value of del v by del x, and again differentiating v partially with respect to y, we get del v by del y is equal to e to the power minus x, then x into cos y minus, we have to use product rule here, so it is minus y sine y plus cos y. So as you have seen in the Milnes-Thomson method, we can take this psi1 of xy is equal to del v by del y, and psi2 of xy is equal to del v by del x. Then on putting x is equal to z and y is equal to 0, we can obtain psi1 of z0 is equal to, so we have to find del v by del y at x is equal to z, y is equal to 0. So this can be obtained from here. So it is given by e to the power minus z, then z into cos 0 is 1, then sin 0 is 0, cos 0 is 1. So it is z minus 1. So this is the value of psi1 of z0, and similarly we can find psi2 of z0, which is nothing but the value of del v by del x at x is equal to z, y is equal to 0. So here we can write 0, so sin 0 is 0, again sin 0 is 0, and this term is 0 because of y. So the final value of psi2 of z0 comes out to be, therefore by Milnes-Thomson method, we can write f of z is equal to integral psi1 of z0 dz plus I times integral psi2 of z0 dz, and plus the constant of integration c. So this is equal to integral psi1 of z0, it is minus z minus 1 dz, plus this integral will become 0 plus the constant of integration c. And after integration we can get the value of this integral as minus z e to the power minus z plus c. So this is your final f of z.